Good evening. Uh, Today we are going into the third part of our chapter, Thermal Properties of Matter. And in this session, we are going to discuss about the different modes of heat transfer. And the first type or mode of heat transfer we will be talking about is conduction. Conduction. Now, you might have noticed if you are, let's say, heating water in a pan with a metallic handle. The bottom of the pan is in direct contact with the burner, with the flame, and you have a handle which is not in direct contact with the flame. But you will notice that after some time, the handle, the metallic handle will start getting hotter or warmer. And this is because the heat is being conducted from the hotter part of the body to the colder part of the body. And that happens because the molecules of the bottom of the pan, which is in direct contact with the flame, gains heat from the flame, increases its kinetic energy, and starts moving faster, thereby colliding with its neighboring molecule and transferring its kinetic energy to the neighboring molecule. And in that manner, transfers the heat or the kinetic energy to the end of the handle. So even though the handle is not under direct flame, it will become hot after some time because of this kind of heat transfer. And this kind of heat transfer is what you call as conduction, which happens between two parts of the same body which are at different temperatures. Now here what I have shown you is a metal rod of length L, PQ. The rod is PQ of length L and area of cross section A. One end of the rod is at a higher temperature. It's in a heat reservoir which is at a temperature Tc, Tc being at a higher temperature. And the other end of the rod is at a lower temperature, Td. This is a heat reservoir at a lower temperature. So because this end is at a higher temperature, heat will now flow from P to Q. Now it is found that H, which is the in steady state means the temperature of the rod, initially this is at a higher temperature, this is at a lower temperature, and heat starts flowing from P to Q. Now after some time you will find that the temperature of the bar decreases uniformly with length, and then you say that the heat transfer is in steady state. So in steady state it is found that the quantity of heat transferred in unit time or the rate of heat flow, which is H, is directly proportional to the difference in temperature between the two ends of the rod. That is, this end of the rod P is at a higher temperature Tc, this end of the rod is at a lower temperature Td. So the difference in temperature between the two ends of the rod is Tc minus Td, and greater the difference in temperature, greater will be the heat transferred in unit time. It's also directly proportional to the area of cross section of the rod. So greater the area of cross section, greater will be the heat transfer. But it is found to be inversely proportional to the length of the rod. Greater the length of the rod, lesser will be the rate of heat flow. Now this can be written as H is equal to K into Tc minus Td by L, where into A here, where K is called the thermal conductivity. It is the constant of proportionality in this case. It is called the thermal conductivity, which will depend on the type of material that you are using. So, for example, you would have noticed that metal vessels, some of these metal vessels used for cooking are given a copper bottom, and the reason why they give it a copper bottom is simply because copper has a very high value of thermal conductivity. It is around thermal conductivity K is 385 joule per second per meter per Kelvin, and for steel it is only around 50.2 joule per second per meter per Kelvin. So if the steel vessels are given a copper bottom, because of its high thermal conductivity, the heat is transferred uniformly and equally all through the bottom of the pan, so that you can have uniform cooking. Steel has a very low thermal conductivity, so the distribution of heat may not be uniform and quick, and therefore we have a copper bottom given to steel vessels to improve your cooking for good distribution of heat. Then the other reason, see, we use plastic foams. It's a bad insulator. Like I told you before, gas is a poor conductor of heat. So if you take plastic foam, there are air pockets, and air being gaseous has it's a bad conductor. So if you have a thermal sheet, a plastic foam sheet, it's a good insulator. When we have offline classes, you will see my tuition class has a below the roof, I've kept a false ceiling. This false ceiling and the roof, in between that, I've kept a plastic foam with these air pockets so that it insulates the sun's radiation falling on the roof, does not enter into a class because I've given it a plastic foam insulation, which is a bad conductor of heat, and your room will relatively remain cooler because this plastic foam is a insulator. It does not allow heat transfer. So that is what we need to discuss under conduction. And now we go on to the second mode of transfer of heat, which we call as the convection. The second mode that we will be discussing. Before I forget, the SI unit of thermal conductivity is joule per second per meter per Kelvin. Joule per second is also, as you know, energy by time is a power. So the other SI unit you can use is watt per meter per Kelvin. Okay, so now we go into the second mode of heat transfer, which we call as the convection. Convection. Now here, you might have noticed that if you are trying to boil water and you take water in a huge steel vessel, you put it on the flame, and you will see that the layer of liquid, convection happens only in fluids. So this layer of liquid or water that is in contact with the bottom of the pan, which is in direct contact with the heat, the flame, will get heated up faster. First it will get heated up, and because it gets heated up, it becomes less dense, and therefore it will rise up on top. So if you have your container like this, if you've taken some liquid here, water, and you're directly supplying heat here. So the bottom of the pan here gets heated up. It heats up the layer of liquid that is in contact with the bottom of the pan. This becomes, as its temperature increases, it becomes less dense, and therefore it rises to the top. When it rises to the top, the colder air on top, the colder water on top, which is more dense, will move down here, and then this gets heated up. When it gets heated up and its temperature increases, it becomes less dense, and that rises up, thus setting up these convection currents. And because of the convection currents, the whole of the fluid gets heated up. So this is another mode of transfer that we call as convection. Natural convection is the reason behind land breeze and sea breeze, which you might have learned in geography in one of your smaller classes. So what happens there is, during the daytime, the land gets heated up faster than the water if you're living close to the ocean. You know that water has a higher specific heat capacity, which we discussed in the last session. So it will take more time to heat up. So during the daytime, land heats up faster, and the air above the land also gets hot, becomes less dense, and moves up. So cold air from the sea blows into the land, and that is what you call as the sea breeze. Now during night, what happens is, water with its higher specific heat capacity takes more time to cool. So land cools faster, the water is still warm, therefore the air above the water is hotter or warmer, becomes less denser, rises up, and the cold air from the land blows into the sea, and that is what you call as the land breeze. So this is natural convection currents that are set up. So this is our second mode of transfer, which we call as convection. We now go into the third mode of transfer, which we call as the radiation. Now in this type of, the third mode of transfer is radiation. And in this type of heat transfer, unlike convection and conduction, radiation does not require a material medium for propagation. The heat transfer is through electromagnetic waves, and about which you will be learning in detail in class 12. So because it does not require a material medium, you know that the light from sun reaches the earth Obviously through electromagnetic radiation, because it has to travel through vast regions of vacuum or space where there is no material medium. So that is the mode of transfer. Radiation is electromagnetic radiation, heat transfer without a material medium. While we discuss radiation, we need to look at what is called as black body radiation. Now, thermal radiations, when it falls on a object or a body, it gets heated up and it starts emitting electromagnetic radiations. Now, a black body is one which absorbs all the electromagnetic radiations falling on it, irrespective of the frequency. Every electromagnetic radiation that's falling on a perfect black body is absorbed. Now, if this black body has to remain in thermal equilibrium, meaning if its temperature has to remain in equilibrium with the surrounding, it has to definitely emit or radiate the same amount of electromagnetic radiation at the same rate. So a perfect black body is an ideal absorber and an ideal emitter because it has to emit the electromagnetic radiations at the same rate as it absorbs. Only then it will remain in thermal equilibrium with the surroundings. So the radiations given out or radiated by a black body is what we call as black body radiation. Now, if you take an enclosure like this with a very small hole here, and let's say it's painted black inside. This is painted black inside. Any light that enters this hole will undergo multiple reflections like this, during which time it will definitely get absorbed by the black paint, and such a body could be, and there is no way for this to escape out of this enclosure, and such a body can be called a black body because light that is entering undergoes multiple reflections on this black paint and eventually gets absorbed. All of the radiation gets absorbed, and so it's a perfect absorber, and that's what you call as a black body. Then when we discuss black body radiation, we need to look at two laws. One is the Wien's displacement law and the other is the Stephens-Boltzmann's law. Wien's displacement law. Here, now suppose we have a black body and it's heated up and it will give out electromagnetic radiations. So we have electromagnetic radiations coming out. And these radiations consist of several wavelengths. So if you now plot a graph with the wavelength along the x-axis and the intensity of these radiations that are emitted by the black body, you find that let's say this is heated to 1000 Kelvin. You see the graph that we get looks something like this at 1000 Kelvin. Okay. So the wavelength that corresponds to the maximum intensity. So we have several wavelengths are being emitted by the body at 1000 Kelvin. But you notice from the graph that at this particular wavelength, there is maximum intensity for that temperature. And that is what you call as the dominant wavelength. So when you heat a body to around 1000 Kelvin, you will see it is red in color. It will emit electromagnetic radiations, but it appears red because even though it is emitting radiations of several wavelengths, the dominant wavelength is that of red color, and that is why it appears red. So let me call this as lambda M1. Now if you further increase the temperature of the body, okay, you will see that the graph obtained looks like this. That means, let's say this is 1500 Kelvin. So you see that the dominant wavelength has become shorter into the shorter region. It has become lesser. So I'll call this as lambda M2. So when you have increased the temperature to 1500 Kelvin, the dominant wavelength decreases from red to around green color. So this body will appear green. So as you increase the temperature, you notice that even though several wavelengths of all these radiations consist of several wavelengths, but the dominant wavelength has shifted to the green region, lower wavelength. If you now further increase it to, let's say, 2000 Kelvin or above, you will see that this dominant wavelength is even lesser. It will go into the blue region, lambda M3. So what we note from here is, we see that the color of the body keeps changing as you increase the temperature. That means the dominant wavelength decreases with increase in temperature. Or we may write the dominant wavelength lambda m is inversely proportional to the temperature of the body, or you may write this as lambda m is equal to B by T, where B is a constant of proportionality called the Wien's constant, whose value is 2.89 into 10 raised to minus 3 meter Kelvin. This constant, you will see lambda is in meters, temperature is in Kelvin, so its SI unit is meter Kelvin. So this is Wien's displacement law, showing you that as you increase the temperature of the body, the dominant wavelength goes on decreasing. The next law that we need to discuss under this is the Bosemans law, which simply says, if Boseman law, which simply says, if you, as you know, all bodies when heated up gives out energy, electromagnetic radiation, and this Stephen-Boltzmann's law says the quantity of heat radiated per unit area per unit time is directly proportional to the fourth power of the temperature of the body, where this temperature is in the absolute scale. So it simply says the quantity of heat radiated by a hot body per unit area per unit time is directly proportional to the square of the temperature of that body, and the temperature being in absolute scale. So today in our session we discussed the three modes of heat transfer: conduction, convection, and radiation. And with this we come to the end of our chapter, Thermal Properties of Matter. Thank you.